Hello everyone, I am Dr. Lachit Saikia from Department of Physics, Dibru College. So here I am going to teach a course on Statistical Mechanics prescribed by Department of Physics, Dibrugarh University. Then the syllabus, the course is for BSc Honours in Physics students. And to show you the details about the course, so the course code as prescribed by the university, this is Physics C-14 and title is Statistical Mechanics, and the total credit assigned for this course is 6 credits, whereas 4 for the theory part and the 2 credits for practicals part. Okay. So the Statistical Mechanics, as you will see and as you will know, that is a very important branch of physics where it deals with the behaviors or the dynamics of the microscopic constituents of the system, and then by looking at the behavior and their dynamics, we like to predict the physical phenomena or try to study how this dynamics and the constituent of of a system actually governs the physical phenomena, or so to say the macroscopic properties of a system that we study in thermodynamics. So here you can see the details about the course structure. The syllabus for the course, it includes classical statistics, classical theory of radiation, quantum theory of radiation, then you have quantum statistics, start with the Bose-Einstein statistics and Fermi-Dirac statistics. So what I have done for this course is that I have rearranged the topic in a certain way which I feel is one of the most, I feel that it's a suitable way to teach to the students, and I thought I will follow that. And needless to say that I have covered all the topics which are prescribed in this syllabus of university. So here's my course plan. Just we have rearranged the terms, in the content of the syllabus. So to start with the classical statistics, we know that the important part, the very basic fundamental, the ingredient for statistics is the probability. We'll know a little about probability. Then we'll slowly go into deep in the subject, microstate, so on and so forth. And then as you can see, this both the syllabus I will upload in the LMS as well. Then we'll have this classical theory of radiation, where we'll study the various theories developed by many scientists for the radiation, which was revelation for the development of quantum physics or quantum theory that we have in the beginning of this 20th century. Then in the quantum statistics, Bose-Einstein to start with, and then Fermi-Dirac statistics. So we'll upload this as well, and then slowly one by one we'll go on learning about this subject.
We shall start discussing about the statistical mechanics. As I had said that this subject, statistical mechanics, deals with the macroscopic properties of the system, where we can think about, temperature, pressure, energy, enthalpy, entropy, and these properties like this. So from the point of view of macroscopic point of view, okay, so basically what we will do, we will understand the basic behavior or the configuration and the dynamics of a system from the macroscopic point of view, to understand how this microscopic dynamics of the constituent of the system governs the macroscopic property. Now, if you think about the system, let's say, so I draw a system, just assume this is my system, and here, so I follow, let's say our system is a very simple system, it consists of only one particle, okay, so it consists of only one particle, let's say. So from the ordinary laws of classical physics, or so to say the Newtonian mechanics, we know that if you know a initial position, let's say x, if we talk about one-dimensional thing, x, and its velocity vx and mass of the particle, then at later time t, we can, at some time later, we can exactly find its configuration if we know what are the force acting on this particle. Okay, all right. Now, the complexity of the problem keeps on increasing if let's say if this system consists of one more particle. So then I will have more number of equations to solve. Now if I keep on increasing this particle, this system consists of, so if you take simple 1 mole of substance, let's say 1 mole of substance if you talk about, okay, so it contains So this system consists of in order of 10 to the power 23 particles or atoms, molecules that you can think about. Okay. Now imagine solving that many equations just to know the system at the very next instant, what its configuration is going to be. So that is not very easy to solve, I mean, using even the supercomputers. So even if you can solve, it will take a lot of time, and that is not, you know, it's not good enough time to invest to just to solve the configuration of the particles at the very next instant, what is going to happen. And then later on to realize that, or to later on to understand how this microscopic dynamics of the particles, you know, govern the macroscopic property of the system. So that's why you can say that to understand these macroscopic properties of a system, you know, which we study in our basic thermodynamics courses, you know, so the ordinary laws of classical physics is not good enough. Okay, it's not suitable, so to say, so we can say that ordinary laws of motions are not suitable to understand or to study the macroscopic property of a dynamical system from the macroscopic point of view, because it needs a lot of time to even solve these equations. Right. Then what is the way out? So how do I approach this? So how do I go about knowing the macroscopic properties of the system from the microscopic point of view? Okay. So there we look for a better approach, or the suitable approach, which we call is from the statistical point of view. So there, what we do in this statistical approach is that, even though, as I said, our system consists of a very large number of particles, let's say, so our system consists of a large number of particles. So what in the statistical approach, in a sense, what we do that, we don't look at how exactly one individual particle is moving or going forward or changing the configuration over time or evolving with time. But we look at the average values or average parameters associated with the system, how that is changing over time. I know the average is being contributed by each of these individual particles, right? So basically, one best example which I always think about is like, so if you see a colony of, let's say, honeybee, okay? So if you look at that system, if it's a colony of honeybees, so each one of them will move in randomly in many directions. If you have observed anytime this colony of, but overall, what they do, if you follow some kind of an imaginary envelope which is surrounding the entire colony of honeybee, so that envelope, okay, if you think, let me see, this is like, so this honeybees, so they move in some direction much slower than how these individual particles or the individual honeybees, they move forward or backward, or the direction it moves forward, right? So that is a way to, you can imagine or you can think about the statistical mechanics. So they don't look at the individual, so to say, the particles dynamics, but how the system is evolving on an average over the time, right? And this statistical approach was applied by scientists like this J.C. Maxwell, Boltzmann, Gibbs, and they're very successful to explain the temperature, pressure, volume, energy associated with system. Okay. However, they could not explain the spectrum they have got that from the black body radiation. Okay. So the black body radiation. So this classical statistical approach could not explain this black body radiation and the specific heat at low temperatures. So they could not explain this low, sorry. So they could not explain the specific heat at low temperatures. So there was some deficiency or some drawback in the theory of this classical statistical approach to understand majorly, and then etc. There are so many other phenomena we'll talk about as we go along the course. So this classical statistical mechanics could not explain this black body radiation and specific heat at low temperatures. So later on, with the development of quantum theory, scientists like Satyendranath Bose, Albert Einstein, Fermi, Paul Dirac, these are people which could successfully come up with the quantum statistical mechanics theory. So quantum statistical mechanics or quantum statistics, and which could explain this black body radiation and the specific heat and many other things. We will see much more interesting things like Bose-Einstein condensation and phenomenon like this. Before we go further, let's discuss some of the basics of statistical mechanics. First thing, we need to know about probability. So probability is defined as number of cases in which the event occurs divided by total number of cases, or in some way we can say that probability is the ratio of number of favorable outcome to total number of outcomes. Right, so this we have studied in our school classes as well. So basically you can think about a event, let's say I name that as A, which occurs in, let's say, a number of ways, okay, small a number of ways, and does not occur, so it occurs in a number of ways, and it does not occur in, let's say, b number of ways. So the event does not occur. Okay. So we know the total number of cases is what? So total number is a plus b. This is the total. Okay. So this is total. Now the probability of the event that A occurs that I can think about is A by A plus B. And let's say the probability in which the probability of not occurring the event is, we can talk about B by A plus B. So, and the total probability, as you all know, that it has to be 1. So probability of occurring the event plus the probability of not occurring the event is going to be always 1. Now let's look at some of the examples of the probability. So the simplest example is the tossing of coin. So we know if we take a fair coin, let's say, so it has got two faces. So we'll know that this is head in one, on two. So if we toss a coin, one of the surface will appear to be head, and if the other one, it will be tail. So now the probability of, so if you toss a coin, single coin, the probability of appearance of head is always, so it's like there are two outcomes, total number of outcomes are 2. In number of cases which event occurs, so we are considering the number of the head appearing on the top. So then this is 1 divided by 2. Similarly, the probability of appearing tail is also same, half. And total probability, as you all know, this is, it will be half plus half, so that will be 1. So another interesting example is throwing a die. The die has got 6 faces, okay, 6 faces, and on each of the faces you have the number inscribed on that. So it's basically it's a dot, okay. So if there's 1 dot, it represents 1. So if there's a 5 dots, that represents 5. So when you throw a die, so there is total number of 6 outcomes, okay. So it could be any of the outcomes that you can see coming up on the top surface. So if I ask what is the probability of getting a number which is 1, so out of 6 there is only one way which the 1 can appear on top. So then total number of outcome is 6. So the probability of getting 1 is 1 by 6, I mean. So now I'm interested in asking, let's say, the probability of getting a number which is less than, let's say, 3. So less than 3, there are two numbers, 1 and 2. So there are 2 ways that event can occur, and there are 4 ways that event will not occur. Okay, so probability of getting a number which is less than 3 will be 2 by 6, and eventually it will be 1 by 3. Okay, so in the same way, if we go about, what is the probability of getting a number 7 on the top surface? In that case, we will have 0 probability, because there is not a single case in which the number 7 will appear on the top surface. So this is regarding the 2 simplest examples that we come across in our earlier school days as well while learning about the probability. Now probability plays a very important role in statistical mechanics. We will see as we go along the course. Next, let's talk about some of the properties or the rules of a probability theory, or it's some of the rules of probability. Now first is additive rule of probability. Okay. Now let's consider let's consider a box, okay, and let's say there are 2 small regions here, okay, 2 small regions here. This is, let's say, region 1, or I could say this is a small volume, delta V1. This is another volume which I am interested in. Let's say this is delta V2, and the total volume of the box is, let's say, V. Okay. So what happens now here in additive law of probability applies to mutually exclusive events. Mutually exclusive events. Meaning, suppose a event A is occurring, that prevents occurrence of the event B. Meaning, let's say I have a particle, okay, so which is, so imagine there is a particle, particle P, let's say, okay, which is entering, so the probability of, so which is entering this delta V1, okay, this region, let's say A. So I define the event where particle P is entering into region A. This is my event A. And even this particle appear entering into B, that is event B. Okay. So now, so event A, I define that the particle going into region this delta V1. Okay. And in second case, event B is particle going into delta V2. Now at the same instant, if the particle is found in region, let's say delta, this case delta V1, so I'm sure, rest assured, I cannot find the particle in delta V2. Okay, so if the event A happens, it is preventing the event B to happen. So in a way, one event is affecting the occurrence of the other event. So event A here, which means that particle P is present in delta V1, is preventing, which is true, right? So the same particle cannot be at the same time, cannot be at two locations. Okay, so these kind of events are known as mutually exclusive events. So in that case, let's say now I do n number of trials. Okay, so what I do, I take n number of trials that this particle P is, I'm throwing the particle into the box, and let's say there are m number of times. Okay, so this particle P enters into, let's say, delta V1. Okay, and let's say n number of times the particle enters into, so the particle n times it's entering into V2. Okay, so the probability of finding the particle, at least in one of these two regions is given by, so that particle is found in delta V1 or V2. In that case, we know that, see, the probability of finding the particle in this region, event A to be happening. So then so I have done n number of trials. In that case, the probability of finding the particle in delta V1 region is m by n. Similarly, the probability of finding the particle in delta V2 is n by n. Total I have done n number of trials, and then out of that m times I find in delta V1, which is event A happening, and n times which is in delta V2 and event B is happening. Okay, so now I want to find out the probability of finding the particle in any one of the region. See, I'm not concerned about if it is going outside there. Yeah, the particle may be outside these two regions because the box is very big. Okay, there are other regions as well. So in that case, these two events are mutually exclusive, and in that case, the total probability or the probability of finding in at least one of these regions, delta V1 and V2, will be given by sum of the individual probabilities, which is equal to n by n. This is m by n. Okay, all right. So similarly, if we have n number of, let's say, the mutually exclusive events, in that case, so if there are many mutually exclusive events, then we can just simply sum up the probabilities to find out the probability that we are interested in, or the probability of finding the particle. I can increase the number of events. Let's say B, C. So B, I have the event C. We have, let's say, probability of finding another region. So the probability of finding the particle in any of these regions, then we can think about, or we can say that the probability of finding, so the total probability is sum of the individual probabilities. So basic idea behind this additive law of probability is that the events has to be mutually exclusive, meaning meaning one event must confirm non-occurrence of the other events. So then only these are mutually exclusive events, and this additive law is applicable only for the mutually exclusive cases. Now, the second case is, let's look at one of the example. Okay, so how do you do about it? So here the example says that a card is drawn from a well shuffled pack of 52 cards. Calculate the probability for this card to be either a king or a queen. Okay, now let's try to solve this problem. So we have total number of 52 cards, right? Out of that, there are how many kings we will find? There are 4 kings, right? So there are 4 kings. So the probability of finding a king, so there are total number of occurrence of the event is what? So event is here finding the king when I draw a card, okay? So then the 4 number of ways that I can find a king, the total number of cards is 52. Okay, so this will give you 1 by 13. Similarly, the probability of getting a queen, that is also there are 4 in number total, so that will be the probability of getting a queen is 4 by, sorry. So this is 1 by 13. So the probability of getting either king or queen will be, so this is mutually exclusive, because if I get a king, I am rest assured that I will not get a queen. So one event is preventing the other to occur. So the probability of getting a king or a queen will be simply sum of the individual 1 plus 13, 1 by 13. So this will be 2 by